So hello everyone. This in this lecture we'll be looking into the other two sets of process scheduling algorithm, which is the round robin process scheduling algorithm and the priority based process scheduling algorithm. So in the previous video we discussed about the first come first serve and shortest job first process scheduling algorithm. In this video, let's start with the third type of process scheduling algorithm, which is the round robin. So, round robin is a process scheduling algorithm and it is a preemptive process scheduling algorithm, which means process will be halted while executing and equal chances will be given to all the process for their execution. So basically what happens in round robin is we have some time quantum that is associated with every process. So this time quantum denotes how much time will be given to each process for its execution. Means for how longer the CPU is given to the process for the execution. So let's say I define time quantum as 2 seconds maybe. So in that case 2 seconds means each process will be given 2 seconds for their execution. So let's say if I have this example with me. So in this example the time quantum, we have three processes first. We have process 1, process 2 and process 3. The burst time of the process are listed and the arrival time are listed. Now all the process has the same arrival time, that means all of them arrive at the same time, which is the 0 millisecond. Now the time quantum is 2 in this case. Now what will happen is 2 seconds or 2 milliseconds basically will be given to each and every process for their execution, so that no process waits for the CPU for a longer amount of time and the problem of starvation can be avoided. So let's say if you look at the figure here, what you see is first at time 0 p1 process, because all process at time 0 p1 p2 p3 all the processes are there. Okay, so we have started with, let's say, the first process only, which is the p1 on the basis of first come first serve. So p1 in this case will be executed for 2 milliseconds because the time quantum is 2. Now for 2 milliseconds it is executed. Now the burst time here is equal to 8. Now P2 will execute for again 2 seconds. Now the burst time is reduced to 3. Now P3 will be given chance and it will be executed. The burst time of now P3 would be 6. And similarly, after the 3 processes executed, again P1 gets the chance to for the execution. Now P1 again executes for 2 milliseconds. So here the time duration is 6 for P1. Similarly, now P2 execute, the time duration is now 1, and now P3 executes, time duration is now again equal to 4. Okay, so again I come to P1 executes, now time duration is equal to 4. Now P2 execute, P2 only has 1 millisecond left, so it executes only for 1 millisecond, though the time quantum allowed to P2 is 2, but it will only execute for 1 millisecond. And then P3 executes for yet another 2 milliseconds. Now the time quantum is reduced to 2. P1 executes again for 2 seconds, time quantum is 2, and now P2 was already finished, so again P3 comes, P3 executes for 2 milliseconds, time quantum 0, and finally P1 comes and P1 again executes for 2 milliseconds. So now here the time quantum is again 0. So in this way each and every process gets the chance to for the execution. Now the average waiting time and turnaround time are calculated in the same way that we have discussed for the first come first serve and the SJF. Okay, now what happened if, let's say, we have different arrival time? Now this example was the processes with the same arrival time, that is 0 milliseconds. Now we have processes with different arrival time, say 0, 1, 2, 4. Now in this case how the scheduling will take place? Now in this case what will happen is each of the process will be maintained with the help of a ready queue. So a ready queue is there which is available, which helps for the processes to maintain their execution. So basically how much process is executed at which how much duration is left for the process, for the execution, how much time is still remaining, how much is that it is executed, everything is maintained with the help of a ready queue. Now let's say we have a ready queue which is defined here. So let's say this is the ready queue here. Okay, now I have this as my ready queue. Okay, this is the ready queue here. So now, and let me again have a Gantt chart, a timeline Gantt chart with me. So maybe this is my Gantt chart. Okay, so what will happen is, first let me have P1 process. Let's start with P1. I have first at 0 millisecond only P1 process is there. Okay, so at 0 millisecond, if I start drawing the ready queue, at 0 millisecond only P1 process is there in the ready queue. Okay, which is ready for the execution. So I have P1 process with me in the ready queue. What I'll do, I'll take this process from here and give the CPU to this process. Okay, so P1 comes and gets the CPU. So this is the ready queue, or you can say this is the running queue. You can say here the uh, processes are having CPU. Okay, so now at 0th millisecond the P1 is removed from the ready queue and it goes into the running queue. Now how much time will it be executed? Since the time quantum is 2 seconds, 2 milliseconds to be precise. Okay, so it runs for 2 milliseconds. So from 0 to 2 P2 will run. So now the burst time of P1 is reduced to 3, right? Now again at 0 millisecond I'll see how many process I have. Now at 0 millisecond I have P2 and P3 both with me. So I write here P2, I write here P3. In the ready queue I have P2, P3, all two process available. Now what will happen is, now I want P2 here. Okay, P2, I want P2 to be in the running queue, but P1 is already running. So what I will do is I will remove this P1 from the running queue and take it back to the ready queue here, and I load the state of P2 here. Now P2 will get the chance to execute, and this process is known as context switching, because what I am doing is I am saving the state of P1 here in the ready queue, because it is not completely executed. P1 still has 3 milliseconds with it left. Okay, it is only executed for 2 milliseconds. So what I do is I extract P1 from here and I put P1 into this ready queue. I load the new process here in the running queue. So I load P2 here in the running queue and I save the old state of P1 and load the new state of P2 here. So this is context switching. So when next time when I load P1, the execution will start at the third, because the execution will start only for 3 milliseconds because it is already executed for 2 milliseconds. So now P2 comes here. P2 is again executed for 2 milliseconds. That means from 2 to 4 it will be executed. Okay, so P2 is removed from here. It comes here. It is executed. Now at 4 milliseconds I also have P4 with me, right? Because at 4 milliseconds P4 also arrive. But in the ready queue the next process that needs the CPU is P3. So I have added P4, but the process which will get the CPU next is P3. So now I load P3 here. Okay, and what I do is I also load the state of P2 here. So again P2 is removed and P3 is added here. So P3 is removed for here. Again P3 runs for 6 milliseconds. Now in the same way, now again the time reduced to 2, P3 again the time reduced to 0. Now again in this case P3 comes here, P3 is gone. Okay, what I will load P1 now. P1 is again a run for 2 milliseconds. So again I cross it and write the time of P1 as 1. Okay, So again, now next would be P4, and P1 will obviously come back here because it has still some time left. So P2 comes here, not P2, my bad, P4 comes here. I've just crossed it. P4 comes here. So P4 is again run for just 1 millisecond. So this is till 9. Now since P4 is finished, so I will no longer add P4 here. Okay, so P4 is no longer needed here, and even I don't have to add the P3 here because P3 was also gone after this. After the completion, P3 was gone, so I no longer have to add it here. So after P4 I only have now P2 with me. So P2 needs 1 milliseconds for its execution. No, P2 needs 2 milliseconds for its execution. So again, it executes for 2 milliseconds. P2 is removed, and finally I have P1 with me, and P1 executes for 1 milliseconds, and again its execution is over. So this is what is a round robin with different arrival time. Okay, in this way we maintain a ready queue and a running queue when we have the round robin with different arrival times. So this, you can see the table here which calculates the turnaround time and the waiting time of different processes. So you see here how you calculate the, let's say, the turnaround time of P1 here. So turnaround time of P1, again the same formula which we have been using, which is the completion time minus the arrival time. So completion time for P1 is 12 milliseconds because P1 got completed at 12 milliseconds, minus its arrival time. P1 arrived at 0 milliseconds, so minus 0 would be 12. Again, turnaround time for P2 is completion time minus arrival time, which is what P2 completed at 11 millisecond, minus its arrival time would be 1. Okay, so that makes it 10. And similarly for P3 and P4 we can calculate. Now the waiting time. Similarly, the waiting time for P1 would be turnaround time minus the burst time. So turnaround time is 12 for P1 minus the burst time of P1 was 5 millisecond, which makes it to 7. Right, so this is how we are calculating the turnaround time and the waiting time of the different processes. Now next thing which is in the pipeline is the code of how you have to implement the round robin algorithm. Now again, this is the steps, the algorithm to implement the round robin process scheduling. Now what we will be doing is, we will be first creating an array which has the burst time of all the processes. So first we have an array bt, okay, which has the burst time listed of all processes. Okay, now one very important thing, the algorithm which we are doing of round robin here, the algorithm here is non-preemptive version, right? We are dealing with the, sorry, so okay, in this case obviously it's not non-preemptive, it's preemptive only, because round robin is obviously preemptive. The next one, which was priority, there we have preemptive and non-preemptive both. There we'll be doing only at the non-preemptive one, but round robin is obviously only preemptive, so here we are only looking at the preemptive version. Okay, and in this case the arrival time of all processes is 0. Okay, we discussed two types. We discussed one with the same arrival time and one with different arrival time. So we'll be implementing this particular form of round robin where the arrival time of all process is 0. Okay, and obviously it's a preemptive version. So how we'll be doing that? We are maintaining a array which is the bt burst time array, which has the burst time of all the processes with it. And then what I will do, I will make a copy of this array and rename is it as remaining burst time. This is again a duplicate array containing the burst time of all processes, but how it will be different is, it will keep the track of the remaining burst time of all process. So with the help of this array, I will be tracking the remaining burst time of all the process, because as you can see in this case, so Like earlier the burst time of P1 was 10, then it got reduced to 8, then 6, then 4, then 2, then 0. So I need some array, something which can store, let's say, the burst time of all process. Maybe in this case for P1 it could store 10, 8, 6, 4, 2, and finally 0. So I need something which could store the remaining burst time of all the processes. So for that we have remaining BT array. Next, I will create another array that will store the waiting time of all the processes, and it will be initialized to 0 first. Now, the idea is what I will be doing. I will be checking the burst time of the process with the time quantum. So let's say if the time quantum is 2 milliseconds as we have used, if the burst time of the process is greater than time quantum, means it has still some time left with it. So what I will do is I will increment the value of time quantum, and I will decrease the value of the remaining burst time by the time quantum, because obviously now when it executes for 2 milliseconds, the burst time will be reduced by 2 milliseconds only. So that's what I will be doing. I will be increasing the time quantum first, the variable t. This is done so that I can have a track of that for how long, for how many times the process got executed, and the remaining burst time stores all the values related to its time quantum, that how much time now is left. Otherwise what would happen is that otherwise we would what we'll do is we'll calculate again, we'll do the same thing, we'll add the remaining time in the time quantum, and we'll also be calculating the waiting time, and we'll be initializing the remaining you can say burst time with the variable 0. Means that the process is over. Now let's see this particular code here. Now, starting off with the main function. So this is the main function here. Again, I have some processes with me, some process ID with me. Variable n is here. So again, in this case, what would be the value of n? N would be size of processes, which is, since there are four processes and each one has 4 size, divided by size of individual process, that is first process. So again the size of first process is 4 only, so 4, this would give me n equal to value as 4, right? So n is 4. We have the burst time of all the process, that is 5, 4, 2, 1. So this is the burst time of all the process, and time quantum here is 2 only. So I have a time quantum as 2 here. Now what will happen is I will now call the function find average time, which is this function, to calculate the average time of all processes. Now let's start with the code here. So now let me first maintain one table. So now this was the function which was called find average time. So this is the function find average time here. So here you can see I have multiple variables declared. I have the waiting time declare, waiting time array is there, total turnaround time array is there. Again the same variables which we have been using in the previous scheduling algorithms. We have the waiting time array, turnaround time array, waiting time variable, and turnaround time variable. And then we have the function that is used to find the waiting time and find the turnaround time. So let me just first go to the find waiting time function. So this is the function to find the waiting time of all the processes. Now what will happen, as I said, I have one array with me which stores the burst time of all the processes. So this particular array, it stores the remaining burst time of the processes. So what I am doing, I am copying the current burst time of all the process into the variable remaining burst time. Okay, and I am initializing current time t with 0. Now I have process P1, P2, P3, P4 with me, okay, with their burst time as 5, 4, 2, 1. So this was the input here which we took from the user, okay, and based on this input now I will calculate the waiting time and the turnaround time. So at t equal to 0, I have initialized the current time at 0. I start off with this while loop. Now this while loop says that there is one integer variable which is done. So initially done is initialized with the value 1. So 1 means if the value of done is 1, then that means that all processes have completed their execution. Okay, so initially we have initialized it with 1. Okay, but as soon as we enter into the loop, we initialize it with 0. That means the process is still pending. Okay, so initially the value of the variable done is again equal to 1. Now I start off with this loop. So again, if I see the indexing here, okay, process indexing, it is 0 1 2 3. So this is the process indexing which would be helpful for us. So again, for starting off with I equal to 0, okay, so for I equal to 0, I see if remaining burst time of 0 process is greater than 0. So the remaining burst time is has now the burst time of all the processes. So the remaining burst time of the first of the zeroth process is greater than 0. That means the remaining burst time, that is 5, is greater than 0 or not. So yes, obviously 5 is greater than 0. Then what I will do, I will initialize the variable done with 0. So done is equal to 0. That means this process is still pending because its burst time is greater than 0. It means it has not completed its execution. Okay, then what I do is I go to this if statement. So I again do if burst time of 0 is greater than quantum. So quantum was 2. So because we are executing each process for 2 milliseconds, so quantum here is 2. So that means 5 is greater than 2. Again, yes, it is greater than 2. What I will do is I will do t is equal to t plus quantum. So now the value of t was 0 initially. So 0 plus quantum. So quantum is 2. So that means 2. So now t is now equal to 2 here, right? And remaining burst time, the remaining burst time of the zeroth process is equal to its previous burst time, which is 5, minus the quantum 2, that will be equal to 3. So the burst time here is 3 for process P1, okay, which is at index 0. Now this loop is finished. So obviously if executed, else will not execute. Now I again come and increment the value of I to 1. Again same thing happens if burst time of one process is greater than 0. So yes, 4 is obviously greater than 0. So what I do, I check the remaining burst time is greater than 2. Yes, so 4 is obviously greater than 2. So what will happen is t will be equal to the previous value of t, that is 2, okay, plus the time quantum, that is 2, it will be equal to 4. And remaining burst time of the first process would be its previous burst time, that is 4, minus the time quantum here. Okay, so minus the value of quantum is again 2, so that will be 2, right? So this is 2 here, and the value of t is updated till 4. Okay, now next again the value of I is incremented. Okay, remaining burst time of 2 is greater than 0. So yes, 2 is obviously greater than 0. I'm talking about this 2 here. Okay, this is obviously greater than 0. Then I check whether it is greater, whether the remaining time value is greater than the value 2, the value of time quantum. So I see here the value is not greater than 2, it is equal to 2. So what will happen is this if will not be executed, and I will come into the else part. So under the else part, what happens is t is equal to t plus remaining time. So t was 4 plus the remaining burst time of this. So remaining burst time of this is again 2. Okay, so this gives me 6. So this is 6 here. Now what happen is of waiting time of this process, that is the second process, is equal to t value, that is 6, minus its burst, minus the value of burst time. It's now this value is the original burst time. of this process. So the original burst time of this process was 2 only. So this is 2, which will give me 4. Okay, so the waiting time of this process, P3 process, is now 4. So I have the waiting time of uh, this process, which is indexed at 2, as 4. Okay, so P3 process, the waiting time is 4. And what I do, I change the remaining burst time of this process as 0. Now the burst time of this process will be 0. Why? Because obviously it was not greater than the time quantum, which means it is less than or equal to the time quantum. So in that case, obviously, because we have time quantum 2, so automatically it will be executed for 2 milliseconds, and the value is again set to 0, and waiting time is also calculated. So in this case, what happened is, this process, the P3 process, is over. Now let's go and switch with the value of I equal to 3. So when I is equal to 3, I see that the remaining burst time of 3 is greater than 0. So I see 1 is greater than 0. Definitely it's greater. So what I do is, I initialize done with the value 0 again. Okay, and the remaining burst time of t is greater than 0. So 1, I see 1 is greater than 2, which is not the case. So again same thing will happen. T will be equal to its previous value, that is 6, plus the remaining burst time of the value 3, that is 1. This will be 7. So this would be 7, because the remaining burst time of this process is 1. And now the waiting time of this process would be the value t, that is 7, minus its burst time, that is 1, which is equal to 6. So its waiting time here is 6, and now the burst time as per this particular step, the burst time would be equal to 0. Okay, so that's how we have calculated the waiting time of these two processes, and these two processes have completed their execution. Now let me just erase these values. So let's erase these values so that we have some space left here. Now we see that process P2 and P3, they have finished their execution. They moved into the else part, and under the else part, as per the complete explanation, they have completed their execution. We have now just P1 and P2 process remaining. Now let's see what happens with them, because they still have 3 milliseconds and 2 milliseconds respectively left with them. So let's just see what happens. Now I was equal to 3, and we had this particular thing that is left. Now again this is done. Now again what we will see, that if I go back here, I see that the value of I is now, earlier it was 0, then it went to 1, then it went to 2, and then it went to 3. Okay, and in that case, the loop, all the process have finished their execution. In that case, what I will do is, I will check if the value of done is equal to 1. So the value of done is not equal to 1, because obviously we still have some process with us remaining. Okay, and that is true. We still have P1 and P2 with us, which are remaining, which have not completed their execution. Now what I will do is, I will again move to this particular loop while, okay, because it has not completed its execution. If the value of done would be 1, then the statement here you see is the break statement, and it would have come out of this loop. But it is not true, so it will again go back to the while loop. It will again set the value of done equal to 1. So again the value of done is 1, and now I again have the value of I with me as 0. So I equal to 0, I see that whether the remaining burst time of the 0th process is greater than 0. So that is, yes, 3 is greater than 0. What I do is, the value of done is equal to 0. The remaining burst time 3 is greater than 2, yes. So what I do is, I add the value of previous value of 2 with the time quantum. So again the value of t is 9 here, and the remaining burst time is reduced by 2. So I have the remaining burst time here as 1. Again, when the value of I is 1, I see the next process, that is 2. So whether 2 is greater than 0, yes. Whether 2 is greater than 2, no. So it will move into the else part. What it will do, it will add the value of t with the remaining burst time, which was 2. So now t is 11, and the waiting time of this process would be the value of t minus its burst time. So minus its burst time is 2. So the waiting time of again this process would be located in this particular case now, and the remaining burst time would be again 0, and the same thing would be again done for the 0th process. So same kind of looping will be there. Okay, and obviously for I equal to 2 and I equal to 3, we will not have this particular loop available, because the burst time here is not obviously greater than 0. So the automatically when we are done, the value of the variable done would be equal to 1, and the processes will come out of this loop. So this is basically a continuous loop till we have all the burst time as 0. When we have all the burst time as 0, the value of done would be equal to 1, and we'll come out of this loop here. Okay, after we come out of this loop, we have come done with the find waiting time function. We now move to the find turnaround time function. So find turnaround time function, what is there in this particular function is, this is the function. So this function calculates the turnaround time. Again, turnaround time is nothing but adding the burst time and the waiting time of all the process. So the burst time is there, the waiting time we have already calculated, we add them to find the turnaround time, and then this is normal display function, which displays all the value, all the details of all the processes. Okay, we again have a loop here, okay, which has the total waiting time, total turnaround time, and we calculate it in a similar way which we have already discussed. Then we calculate the average waiting time and the average turnaround time of the processes. So the entire computation rest is same that we have already discussed with the previous process scheduling algorithms. So this was the round robin version of process scheduling, and round robin is a preemptive process scheduling algorithm, because obviously you need the CPU, you need to halt the execution of the process so that CPU can be given to other processes for some other time duration. So now next process scheduling algorithm which we will discuss is the priority process scheduling algorithm. Now priority scheduling algorithm is the scheduling algorithm which is both preemptive and non-preemptive. So this priority scheduling algorithm has two versions. One is preemptive and another is non-preemptive. So obviously under the preemptive version, the process will be preemptive from its execution. Under the non-preemptive one, it will not be preemptive, and it will only leave the CPU when the execution of the process is completed. Now under the priority scheduling, each process is given some priority attached to it. So the process which has the highest priority is executed first. So in this way we avoid the problem of starvation, because we start giving priority to a process, and let's say if there is one process that has low priority and it is not able to execute because the priority is low, and there are still many processes left that has high priority and they are executing before them. So what we can do is we can increase the priority of that process and make the CPU available for that. So that process is aging, that we are increasing the priority of that particular algorithm, of that particular process. So these are the steps under the priority based scheduling algorithm. So you start the program, we'll be inputting the number of processes, the burst time and priority of each process, then we'll be sorting them on the basis of priority. So this is the most important step. So priority scheduling is in itself it's an easy scheduling algorithm. The only thing here is that again we'll be sorting the processes. So this is the same way that we have done under the shortest job first. Under the shortest job also we have sorted the programs based on their burst time. Okay, so in the same way, in the under the priority scheduling algorithm also, we'll be sorting the elements, sorting the processes on the basis of their priority that is given to them, and then based on that we'll be printing the order of their execution with the timestamp. So let's first see some one example related to the priority scheduling. Let's say I have some processes with me. I have three processes with me, P1, P2 and P3. Okay, and I have the burst time with me as well as the priority with me. Okay, so what I do is this is 10, this is 5, this is 8, and this is 2, this is 0, this is 1. Now, how do I create a Gantt chart of this? So, this is my Gantt chart. Now, what I will do is I will see what is the priority of each process. So, the priority of the processes are listed here. The process with the highest priority is executed first. So, this is executed first. That means here the highest priority is given to P1. So, I will select P1 for its execution. So, P1 is there, and I'm assuming that all processes arrive at the same time, right? So this is the obviously the assumption that all processes have arrived at the same time. So P1 is there, P1 as priority 2, and it will be executed till 10 milliseconds if I talk about the non-preemptive version. And obviously we'll be implementing the non-preemptive version of the priority scheduling. That's why I'm explaining only the non-preemptive version of the priority scheduling. Okay, so again under the non-preemptive one, pretty simple, it will be executed for 10 milliseconds. Then I again see the priority of next process, which is P3, because P3 has again more priority as compared to P2. So P3 comes and it is executed for 8 milliseconds, so that means 18. And finally process P2 comes and it is executed for 5 milliseconds, that makes it 23. So that's how this is the Gantt chart of the priority based scheduling algorithm. That's how the processes are scheduled. So what we'll be doing, we'll be implementing this only, the non-preemptive version. We will be having the process ID with us. We have the burst time of the processes with us, and then we have the priority of the processes with us. Again, the same thing, we need to calculate the average turnaround time, the average waiting time, and obviously the individual turnaround time and the waiting time of each process. So let's start here. So again, the logic here is pretty much simple. We have, let's say, the process. Again, let me draw this. We have the process, we have the burst time, and we have the priority associated with every process. So we had three processes with burst time as 10, 5, 8, and this is the priority. So what I do, I start with the main function. I enter the number of process. So number of process here is 3, n is equal to 3. I have an array which is the burst time, which stores the burst time. Then I have one more array, the priority based array, and then I have another array, that is the index array. Also these three arrays are there, and then I start with a loop. So the loop says they enter the burst time and priority value for each process. So you see I'm taking the burst time and the priority for each process. So again, the burst time 10 2 would be input from the user, 5 0 would be another input from the user, 8 1 would be another input from the user. So that's how I take the input from the user. So next what I do is I start another loop. So this another loop is from I equal to 0 till I is less than n, that is I is less than 3. So what I do is I take the value of I equal to 0 first. So I is equal to 0. Now I is equal to 0. I have another variable here defined, that is temp. So temp is equal to priority of the 0th process. Again the indexing would be, let me now change the color so that it is indexing is from 0 1 2, right? So the value of temp here would be priority of I, that is 0, because I is 0 here. So the value of temp here is now 2, right, because the priority of the zeroth process is 2 here. So the temp is equal to 2. Now what I do is I see the value of m is equal to I. So there is another variable m which is equal to I, and I is 0 here. Okay, now let's see what are the next step. Next step says that run another loop which is from j equal to I till j is less than n. So j is equal to I means j is equal to 0, and yes, 0 is less than 3. Now what I do, I check. Now this particular loop says if priority of the zeroth, the j is greater than temp. Okay, greater than temp means greater than 2. Okay, so what I do is I set the value of temp equal to the priority of j, but here in this case the priority of 0 which is 2 is greater than 2. This is not the case, so this will not execute. Now what we'll do is we'll again go back to this for loop. J would be incremented and the value of j would be 1. I now check that the priority of 1 is greater than 2. So 0 is greater than 2, no, again same thing. I value of j is incremented. I check priority of the second index is greater than 2, no, 1 is not greater than 2. Again this particular loop is now not executed, and I come to this outer loop here, the I loop. Now what will happen is the value of I would be now incremented. So the value of I would be now equal to 1. Okay, so now the value of I is equal to 1. In that case, temp would be equal to priority of I. So priority of I, now again the value of temp would be changed. So temp would be now this value, that is the zeroth value. So the value of temp would be now 0 because temp is now changed, and m is also equal to 1. Now again the loop start. Again there is some j value. J is equal to again 0. I see priority of the zeroth index, that is priority of the zeroth index, that is 2. Is it greater than temp? Yes. Now I finally found something which is greater than 2. So I finally found something which is again 2 is greater than 0, which is acceptable. Now what will happen is, since under this loop what I'll do is I'll write temp would be priority of 0. So temp would be set to the priority, that is 2. Okay, so priority, because j is 0, so priority of 0 is this 2, so temp would be equal to 2, and m would be equal to j. So j is 0, so m would be equal to 0. So now temp has the revised value with me, that is 2. Now again j would be equal to 1. Okay, j is equal to 1. Now priority of I, that is this value 0, is it greater than temp? No, this is not greater than temp, so it will not go here. Again in that particular case, now what will happen, in this particular case we'll have the value of j to be incremented. J is again equal to 2. Okay, and if that is true, if j is equal to 2, now in that case I'll again check whether the value of the priority of j is greater than 2. So this one, is it greater than 2? No. Again this particular thing is not implemented, and then this particular loop gets finished. Right, now what exactly am I doing in this particular cases? I am basically sorting my array in such a way that I have the priority defined with me. I am sorting it on the basis of the priority. Okay, because you see the swap function here. Okay, so what this swap function is doing, this swap function is taking two values, that is one is the I and second is the m. And if you see here, m was having some value, earlier it was having 0 value, then it was having the ith value, and so on and so forth. So exactly what I am doing is I want to swap the complete you can say process here on the basis of their priority. Okay, that the process which has the highest priority comes first, and then process with the least priority comes last. So that's how I will be swapping. So this is the swap function which is defined here, which is basically swapping. So again the same, because now here in this case I am using pointers. Okay, I am using pointers. So in this particular case, what will happen is I can swap the integer values also, as well as this p1, p2, which are the characters value. The Let me just check the character values also, which I have just taken. So this is the priority, yes. So priority, the burst time, the processes, everything, and as well as the indexing also. So here basically what I am doing, I am just swapping them. Now finally comes the order of execution, that what would be the order in which they would be executed. So you can see here that the order of their execution would be p1, p3 and p2. So the order is, you can see here, the p1, okay, because it has the highest priority. So basically after completing all this, what I will be getting as the final result. Final result would be p1, P3 and P2. This would be the final result. Then I would have the burst time and the priority listed. The burst time of P1 is 10 and 2. The burst time of P3 is 8, 1, and the burst time of P2 is 5 and 0. Right? So basically what we did, we swapped P2 and P3. Okay, we didn't swap previously. As soon as the priority was greater, we didn't swap. Whenever the priority would be lower, in that case we would be swapped. So let's say the I value would be, in this case, maybe 1, the m value can be 2. So what I will be doing, I will be swapping the priority which is there at the 1 index position with the priority at the 2nd index position. I will be swapping the burst time which is there at the 1st index position with the burst time which is at the 2nd index position, and obviously I will be swapping the indexing, the 1st and 2nd index. So after the swapping, I will get this as my final result. So this would be my final result. And when I get this as the final result, what exactly will happen is I have the order of execution with me. Now I will be printing what exactly the order of my execution is. So the order of execution would be P1, P2, sorry, P3 and P2. This would be printed. The indexing, the time, the burst time, everything would be printed. And then here in this particular case, I am displaying my particular processes with their burst time and waiting time. So this is the whole displaying thing. I have initialized two variables, the waiting time which is equal to 0 and the total waiting time which is also equal to 0. Okay, then I start off with one loop. Okay, and this loop is doing what? It is calculating the total waiting time, which is equal to the waiting time plus the total waiting time. So this particular which notation which I am assuming that you people know is equal to the total waiting time is equal to total wait time plus the wait time. Okay, similarly this particular notation is wait time is equal to wait time plus burst of I. Okay, so basically what exactly is happening, I have opted for a loop. There is one loop, so I is equal to 0. Where what I will do is I will again start off with the value where I will be adding the total waiting time with the previous waiting time, and I will be getting both the value, the total waiting time as well as the waiting time. So how this is done? Let's suppose the total waiting time is initially 0. So this is the case, it is 0. Okay, plus the waiting time which is also equal to 0, because these two things are previously 0. So the total waiting time is 0. But under the next statement, you see waiting time is equal to waiting time plus the burst time. So waiting time is again 0 plus the burst time of the ith process. So the burst time of P1 was 10, P3 was 8 and P2 was 5. So this would be 0 plus the burst time of the first process, that is 10. So this would be 10. Now what will happen is this is when I is equal to 0. When I is equal to 1, what will happen is, now again total waiting time, let me just change the color. Now when I is equal to 1, what will happen is, again this particular two statements will be executed. Total waiting time is equal to previous total waiting time. Okay, so previous was 0 only, so that is 0 plus the value of wait time. Now the value of wait time is now 10, so this is 10 here. Okay, so the value here is 10. Now what will happen is, next line, waiting time is equal to waiting time plus the burst time. So waiting time here is equal to, now what is the value of the waiting time here? So waiting time was 10 earlier plus the burst time of the second process, which is 8. So here this is 8, so 10 plus 8, this gives me 18. So here the value is 18 here. Okay, now next, what happens when I is equal to 3? So let me just change the color again and put the value of I is equal to 3. So when, sorry, I is equal to 2. So when I is equal to 2, what happen is, I have the total waiting time with me. So total waiting time plus the waiting time. So total waiting time was 10. So I write here as 10 plus the waiting time. So the waiting time was 18. So this is 18, which gives me 28. Now again, I equal to 2 mein waiting time is equal to waiting time plus its burst time. So waiting time is equal to 18 because earlier it was 18 plus the burst time, that is 5. So again we have 18 plus 5, and which brings me to again 23. Okay, so now if you see these values 23, 18, so earlier, so you see 18 to 18 here, you see 23 here, and earlier it was 10 and then 0. So these value 10, 0, 10, 18, 23 are exactly the same that we calculated here, 0, 10, 18, 23. Okay, which is nothing but the finish time, that when the, how much time the process waited, how much time it at how much time it got completed. So all the values are getting stored here, right? So the waiting time, so you can see, if you calculate the waiting time of, let's say, waiting time of process P3 here. So the waiting time of, let's say, process P3 would be equal to its turnaround time minus the burst time. Okay, or if I don't even consider this equation, I can simply say that P3 waited for exactly 10 milliseconds, P2 waited for 18 plus 10, 28 milliseconds. So that's how they have waited. So we have again these values 0, 10, 18, 23. Okay, this is the waiting time, and the total waiting time would obviously, and this particular thing, this particular variable is storing the total waiting time. And similarly, I can now calculate the average waiting time of all the processes. I can now calculate the average turnaround time for the processes. Now the turnaround time is calculated here. Now let me again erase some of the things which are here. Let me just erase everything. Okay, so now turnaround time is calculated in this particular way. Again, I have the processes P1, P2, P3 with me. Sorry, P1, P2, P3 with me. Okay, and again, if I see in the sorted way, it would be P1, P3, and P2. Okay, and the burst time would be P1, 10, 8, and 5. So this is the burst time. Now the turnaround time, now again the same formula saying that the turnaround time is equal to the total turnaround time is total turnaround time plus the burst time. Okay, so if you see the value of total turnaround time is 0, so total turnaround time is 0 plus the burst time of the 0th process, that is 10. So this is 10. Okay, then if I is equal to 1, the total turnaround time is previous turnaround time, which is 10, plus the burst time here, that is 8. Okay, so which is 80. Now the turnaround time of the third process, it's the total turnaround time 18 plus 5 again. Okay, which brings it to 23. So again we have the value of the turnaround time also. And similarly we can calculate the average turnaround time. Okay, and we are finally printing the average turnaround time, the average waiting time, as well as the waiting time of the individual process also. So output may you have the process index, the burst time, as well as the waiting time of all the processes. So this was the priority based scheduling. It was the non preemptive version of the priority based scheduling, and here I have assumed that the arrival time of all the processes would be 0. And it's a non-preemptive version. So this was priority, and the previous one was the round robin process scheduling algorithm. So with this, I hope you are clear with these two algorithms also, round robin and priority scheduling. Just quickly giving you a brief of all the four types of algorithms that we have discussed. One was the FCFS, which was the first come first serve. So if you remember, this was the first algorithm, first come first serve. So here this first come first serve is definitely non-preemptive. Okay, you cannot preempt a process. So and we have assumed the arrival time of all processes as 0 here. So the code which we discussed the non-preemptive version with the arrival time as 0, and the order in which the process comes, they are executed in that particular order only. Under the shortest job first, we see the burst time of all process, and the process which has the least burst time gets more and more priority. And here we have seen one example with different arrival time. Okay, and again the shortest job also, we have implemented this particular process with the burst time and the arrival time, but we have make a check only on the burst time, and we have sorted them on the basis of burst time only. So the process with the lowest burst time is again executed first, and we have sorted them, and then we have again executed them. This was the shortest job first, and next was the round robin, which was the preemptive scheduling. We have discussed the code of the preemptive version of the round robin. In round robin, we give a time quantum to every process for its execution. A time quantum is given. So we have seen the round robin with different arrival rates, as well as one with the same arrival rate. We have discussed both the things, but while implementing, we have implemented round robin process with 0 arrival rate. That means each of the process had the same arrival rate, which is 0. And finally, we discuss the priority based scheduling algorithm. So priority based scheduling algorithm is of two types, the preemptive version as well as the non preemptive version. And the priority scheduling algorithm, there is a priority that is associated with every process. The process that has the highest priority gets more and more advantage, it is executed first, and the process which has the least priority gets executed at the last. And this is of two times, preemptive as well as non-preemptive. We have only discussed and we have implemented the non-preemptive version of the priority scheduling. We have not seen the preemptive version, not implemented the preemptive version. This was the non-preemptive version of the priority based scheduling. So these are the four most important algorithms, scheduling algorithms, when it comes to the process scheduling section under the operating systems. And these four are the more important scheduling algorithms for your labs. That's why I've covered all the four algorithms here, with along with their source code. So the main idea of this particular video was to get you what to explain you the source code of each and every process here. So this was the main idea. So I hope that you got some understanding about the code, the working of all the four process scheduling algorithm. I would like to say that it's better if you run